So in the previous lecture, so now we are going to start lecture 2. In the previous lecture, we had used three different methods: northwest corner rule, the matrix minima method, and VAM or the penalty method to find the initial basic feasible solutions. Okay, now what are the primary conditions for an initial basic feasible solution? So there are four conditions. The first condition is that the row column constraints are satisfied. That means total supply is equal to total demand, which indicates a balanced transportation problem. So until and unless it is a balanced transportation problem, you cannot find out the initial basic feasible solution. The non-negativity criterion, that means the cost or the units or the quantities which are going to be transported should be always greater than equal to 0. That means this xij will be obviously greater than 0, greater than equal to 0. That is what we mean by non-negativity. And the Cij will be also greater than equal to 0. So practically these two can't be negative because cost can be negative and the quantities which are being transported cannot be also negative. So this is something we say the non-negativity criterion is satisfied. Actually in operation research all the mm, constants we deal with are most of them are non-negative. Okay, the allocations are independent of each other and they do not form a loop. So this is the main attraction of this lecture today. What do we mean by loop and how they are formed? How do we break the loop? What happens when a loop is found in the initial basic feasible solution? So this is what we'll be discussing today. And there are exactly m plus n minus 1 number of allocations. So see that I hope that you will understand. Sorry. Say this is 4, this is 3, this is 2, this is 1, 5, 6, 7, whatever you wish. 9, 10, 1, 2, 3, 5. So I have just designed a transportation problem. Let us see, there are some allocations here. I am not writing the quantities. See how many allocations are here. This is the first, this is the second, this is the third, this is the fourth, this is the fifth, and this is the sixth. So there are 6 allocations. Now what do we mean by m plus n minus 1 allocations? What do we mean by that? M is a number of row, m is the number of supply points. How many supply points are there? 1, 2, 3 and 4. How many how many demand points are there? How many columns are there? There are 4 columns. Actually what I have done here, this can't be a transportation problem. Actually in transportation problem the number of rows and the number of columns are generally not equal. Okay, you'll see in assignment that the number of rows and the number of columns are equal. But in transportation problem you will see that the number of rows and number of columns are not equal. So what we'll do, we'll just add up a column here and we will just allocate one more. So the number of allocations, I hope you are understanding what I am trying to say. Generally in transportation problems the number of rows and the number of columns are not equal. This is a special case where the it is called as an assignment problem. In assignment problem, the number of rows and the number of columns are equal. But generally, in transportation problems, we don't see that the number of rows and the number of columns are equal. But it is possible, but we do not generally encounter such problems. This is why I am just saying. So what I did, I just entered a new column. So how many columns are here? There are now 5 columns. So 5 columns. How many rows are there? 4 rows. So what do we mean by this m plus n minus 1? M is the number of supply points or the number of rows. So it is 4. What do you mean by this n? N is the number of columns or the demand points we are talking about. 4 plus 5 minus 1. So according to the rule, according to the conditions for initial basic feasible solution, there has to be 8 allocations. But here we have just 1, 2, 3, 4, 5, 6, 7 allocations. Okay, we have just 7 allocation. So if we get a problem like this, if we get a solution like this, then we can say we haven't reached the initial basic feasible solution. There is a solution hidden here. Okay, we'll deal with that in a later part. What do you mean by this word hidden and how it is hidden in this solution? We'll deal with in the later part of this lecture. But you just remember that the number of allocations has to be equal with m plus n minus 1. So m is the number of rows or the number of supply points, n is the number of columns or the number of demand points, m plus n minus 1. So this has to be satisfied always. Okay, until and unless it is not satisfied, we cannot say that we have found the initial basic feasible solution. Okay, okay, then let us see what do we mean by loop formation. See, this is a screenshot of a problem. This screenshot, um, it is available in the internet. Now see, the number of, let us just calculate the number of supply points. There are 3 supply points. There are 4 demand points. So number of supply points equal to 3, number of demand points equal to 4. So the number of allocation should be equal to 6. Now see, what are the number of allocations? 1, 2, 3, 4, 5, 6, 7. Now here we can see that there are 7 allocations. So it is more than the 6 allocation which was prescribed in the previous description. Okay. Now when you find that there are more than m plus n minus 1 allocations, you have to understand there are some solutions which are dependent of each other. They are not independent of each other. Now on that case we can say there is a loop present in this solution. You have to find this loop. How do we understand that there is a loop? The number of allocations is greater than m plus n minus 1. Okay, in either ways you can also find loop, but that is from the geometrical perspective, which I'll be saying in later afterwards. But whenever you see that there are more than m plus n minus 1 allocations, you are 100% you have to be 100% sure that there is a loop present. Now what do you mean by loop? So you have to start from a certain allocation. Like here you can see that So here you have to see that starting from this allocation, you move on to this allocation. Then you move on to this allocation. Then you go on to this allocation. And then you go on to this allocation. So a rectangular closed loop has been formed here. A rectangular closed loop has been formed here. So this means that there are solutions which is not dependent on each other. Okay, they're not independent actually. So they are dependent of each other. Okay, so loop means that there is obviously a dependence present between the allocations. So if there is more than m plus n minus 1 allocations or solutions, then there is a loop present. The loop has to be broken. The loop has to be broken so that we maintain the conditions of initial basic feasible solution. Okay, so let us see how do we break the loop, how we can break the loop. Okay, now this is what here, see, in both the cases the loops are present. Okay, now what is depicted in this image, a single quantity has been increased here. Now when this single quantity is increased, obviously 30 was previously allocated, it was 10 earlier, it was 10 earlier, and it was 10 earlier. Now what has happened here, when you have just allocated one more, it becomes 11. Obviously it has to be 29 to maintain this supply constraint. Similarly, when you allocate one more here, this will be reduced by 1 because you have to maintain this demand here. Similarly, when it is getting reduced by 1, there has to be a increase here. So this is the point. This is the point I am trying to say. Now, when this, what is the effect of this total change? You are increasing the transportation of quantity by 1 unit. So the cost increases by 4. Here you are reducing the transportation quantity by unit 1. So it means the cost also reduces, because for a single unit of transportation unit the cost is 5. So you have reduced by 1, so the reduction in cost is 5. We indicate by a minus there, 4 minus 5. Similarly there is an increase, but the cost is here 8. So you have to add up this cost, and here there is a reduction in the quantity of transportation, so it will be 8 also. Okay, so ultimately the change is -1. So when you are increasing the quantity of transportation by a single unit, here you can see there is a change of -1. That means there is the cost is reduced by 1 per unit, change of the transportation quantity starting from here. Now if if you go on if you go on increasing, so the if you convert this 11 into 12, what will happen? It will be, there will be 2 multiplication here. If you go on changing this 11 into 13, what will happen? This 2 will change 3. Similarly, when you are going to make it 20, if you make it 20, then it will be also 20. Okay, let's just remove this part. So when you are going to make it 20, this will also become 20, and this will also become 20. Now see what is the ultimate change in cost. Okay, so here this 10 is getting reduced, so 40 minus 50 plus 80 minus 80, just similar to what if we had written 10 into this, then it would have been minus 10. Here it is also minus 10. So for the change of single unit, this is the change. For the cost, for the change of 10 units, you're just multiplying by 10. Okay, now using this idea, what happens that the number of allocations have been reduced. See, when we have allocated 20 here, it becomes 0. It becomes 0. So there is no need of allocation here. So the number of allocations gets reduced from 7 to 6, which is following the m plus n minus 1 rule. Okay, so you have done two things here. You have broken the loop. You are now following the m plus n minus 1 rule, and the overall cost has been reduced by 10 units. So you have achieved three things. You have broken the loop, you are now following the m plus n minus 1 rule, and the ultimate cost is getting reduced by 10 units. Okay, so similarly, if you do the opposite here, you will see the cost is getting reduced by 1. Here you are also achieving the three things which I was just saying earlier. The loop has been broken. Now it is following the m plus n minus 1 rule, but the change in the cost is positive, positive 10. That means here we are just adding up here we are just reducing. So this was 10 earlier, now we have made it 9. So this was 10 earlier, now it has become 11. Similarly, it was 10, but it has become, it was 10, it was 30. So because of this is change, the ultimate change in is that minus 4, because you are reducing by a single quantity. That means for the transportation of single quantity, you are saving rupees 4, but you are adding up rupees 5 here, and you are adding up rupees 8 here, and here you are saying you are saving 8. Okay, so ultimately the change is positive. So you are achieving the same things, but in an opposite way. In the first case, in this case, the change in the cost, the change in cost was negative, but here it is positive. So this is the difference. So which one will you prefer? Obviously this negative change, because your whole objective is to reduce, is to minimize the transportation cost. So whenever you are going to break this loop, you have to keep in mind that the ultimate change should be negative. You are not going to apply some positive change to break the loop. So this has to be keep in mind. So this has to be kept in mind. Sorry. uh, Now, so this is the thing. So you have to break the loop, you have to maintain the m plus 1 minus rule, and you have to see that the ultimate change in cost is negative, so that the cost is ultimately reduced. Okay, so you can break the loops in two different ways, so that negative change is occurring or positive change is occurring. Okay, but you must always prefer the negative one. Now here comes a very interesting problem. Okay, see, mm, we are going to So here, let us see this problem. Here we can see that there are 1, 2, 3, 4, 5, 6. The number of allocations are 6. M plus n minus 1, that means 3 plus 4 minus 1. This is equal to 6. So it is following the m plus n minus 1 rule. But what is the problem here? There is a loop present. So you have to break this loop. Now when you are going to break this loop, what will happen? Let us see if we break this loop. Let us see what happens when we are going to break this loop. Okay, so here we write 4 6. This 4 6 represents the cost of transportation of a single unit. Okay, so I have written these things. Now it will be 10 here, it will be 10 here, 30, 50, 30, 20. Okay, I'm not writing the supply and the demand materials. I'll just take this data from here. Okay, see, there is a loop present here, from here, here, and here. So there is a loop present. So now what you can do, you can try to reduce this cost. So what you will do, you will just add 1 here. So let's just see what is the change in cost. So plus 4, because you are adding up here, so obviously this will be 9. So minus 6, and here it will be minus 8, and here it will be plus 7. So ultimately you are saving up 3 rupees per unit. So let's just do it for the whole. That means we are going to change the whole allocation. Okay, now how we can do that? Sorry, let's just create up. So it was earlier 10 and here it was 10, so you're just adding it up, 20. So when we make this 20 and it was the supply was 40, so this has to be changed. This has to be changed. This will be obviously 20. Okay, and this as this will also change because 10 units will be added up here. So now see what has happened. 1 2 3 4 5, but you have achieved 5 solutions, okay, or 5 allocations, but you have broken the loop. So that's one thing you have achieved. And another thing is that you have reduced the transportation cost. So now what is the troublemaking part? The important thing is that you are violating the m plus n minus 1 rule. So are you really violating it? No. it is a special case which you term as degenerate basic feasible solution. Now how do you identify it? We identify by an epsilon sign. This means that there is an allocation present, but the quantity of allocation is nothing but 0. Okay, so you have allocated 0 quantity here, and it is not changing your whole transportation cost. So this type of case is called a degenerate basic feasible solution. Now see, the the total number of allocations are now changing from 5 to 6. This is what I am trying to say. Okay, so now you have broken the loop. You are now following the m plus n minus 1 rule, and the total cost of transportation has also reduced. So you have achieved these three things, and this is a special case which we call as degenerate basic feasible solution. And whenever there is a degenerate basic feasible solution, we just give an epsilon sign. Epsilon. Okay, it means 0 allocation. The quantity of allocation is 0, is nothing but 0. Okay, so hope you have understood what do we mean by degenerate basic feasible solutions. Okay, so let us move on. So this is what I was just saying. See, the solution we just made earlier, here it is depicted. See, this is the important thing. This is what we mean by degenerate basic feasible solution. So 0, the quantity of allocation is 0. So you are not transporting something here, but for the mathematical perspective, you are just allocating some number to it, and this number is nothing but 0. Okay, so that the rule of m plus n minus 1 is followed up. Okay, now we'll be uh, trying to solve this problem by Modi method. Okay. Okay. Oh, I think let's leave it here. We'll be solving a problem, starting from we'll be solving a problem in the next class, in the next lecture, where we'll start from the we'll start. Okay, that means we'll find the initial basic feasible solution, then we'll go on optimizing it. Before that, okay, just leave it here. Okay, so let's hope that you have understood all these things. In the next lecture, we'll be discussing about what do you mean by Modi method and how do we optimize a solution using this Modi method. Okay. Okay. So goodbye. Stay safe and keep studying.